Hello, everyone, and welcome. My name is Jennifer Nyman. I'm a principal at Geosyntech Consultants, the coordinator of the webinar series on behalf of SERDP and ESTCP. Today's webinar will consist of a brief overview of SERDP and ESTCP, followed by a technical presentation featuring DoD-funded research efforts to improve and enhance microgrid solutions on military installations. The technical content will be presented by Dave Altman, an engineering fellow in Raytheon Integrated Defense Systems Advanced Technology Programs. We will follow his technical presentation with a question and answer session. The next several slides provide some instructions to optimize your webinar experience. If you haven't done so, download Zoom at the link shown here. If you can't download Zoom, you can view the slides using an internet browser like Firefox, IE, or Edge, and by creating a free Zoom account. If you can't view the slides or if your screen freezes, you can try keying Control and F5 to perform a hard refresh. And then on Zoom, if you are accessing the audio through your computer, you can click the arrow next to the Join Audio button and select Test, Speaker, and Microphone and follow the prompts. If you continue to experience any difficulties with Zoom, please call into the conference line here. You can also submit a comment using the chat box. Please use that chat box, though, only for comments related to technical difficulties. The Q&A option will be reserved for questions for the speaker. In case of continued technical difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration email. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Today's broadcast is listen only. You can submit questions, though, by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. And in fact, we encourage you to submit questions in advance of the Q&A session. When you submit a question, please add your organizational name at the end of the question. And with that, I would like to introduce Mr. Timothy Chatro, who is the ESTCP Program Manager for Installation Energy and Water. Before joining SERDP and ESTCP, Tim worked at the National Renewable Energy Lab, where he focused on energy efficiency and renewable energy project development for the federal sector. Tim, please proceed.
Thank you, Jennifer. And welcome everybody to today's SERDP ESTCP webinar. I'm going to give a few slides of background on the programs and then hand it back to get into the actual fun stuff. But SERDP is the Strategic Environmental Research and Development Program established in '91 by Congress as a partnership between DoD, the Department of Energy, and EPA. SERDP's mission is to identify and address high priority environmental science and technology opportunities, focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies from the lab into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of SERDP research occurring in the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally there will be some supporting lab efforts conducted as part of their projects. There are 4 program areas in SERDP and 5 in ESTCP. The Installation Energy and Water program is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapons systems and platforms are both SERDP and ESTCP programs managed jointly by a designated program manager. Today's webinar presents results from research and demonstration efforts that were conducted under the Installation Energy and Water program. which is focused on improving installations, energy and water efficiency, and improving energy and water security. And here we have our kind of technology categories organized in these three major focus areas: smart, secure installation energy management, efficient integrated buildings and components, and distributed generation. Our webinar series highlights research and demonstration efforts from each of the 5 program areas. And here is our upcoming our calendar of upcoming webinars. You can see a broad range of topics here, including PFAS source zones and analysis, pathogen exposure pathways, energetic materials and munitions, ecosystem models. You can find additional information about upcoming webinars at this link here, as well as a recorded copy of today's webinar. And additionally, I'd like you to ask that you take a moment to fill out a survey at the end of the webinar. It helps us kind of improve the way we manage and implement our webcasts, and that's very helpful to us. And finally, I would like to remind you to save the date for the upcoming, or for the 2021 SERDP ESTCP Symposium, which will be held in person November 30 through December 3rd. This event showcases the latest technologies that enhance DoD's mission through improved environmental and energy performance. With that, I'll hand it back to Jennifer, and I hope you enjoyed today's webinar. Thank you.
Thank you so much, Tim. It's now my pleasure to introduce our speaker for today. Dave Altman is an engineering fellow in Raytheon Integrated Defense Systems Advanced Technology Programs, where his work focuses on the development of advanced defense system technologies. This has included recent efforts that are focused on developing and demonstrating energy storage-centric cybersecure microgrids at Department of Defense facilities. Dave has authored 25 peer-reviewed technical publications and holds 14 US patents. He earned his master's degree from Boston University. Dave, please proceed with today's technical presentation.
Thanks, Jennifer. Thanks to all the folks who've decided to show up. I see we have 99, so that's pretty good. I was nervous that you won't get a big audience, but yes, I work for Raytheon Missiles and Defense. I am in Massachusetts. We have a group that work on microgrids for DoD installations, have been doing this work for about 10 years. And this project, I will say this specific contract wrapped up in October of 2021, but we're still working with the installation to and ESTCP to continue to operate the system, and also continue to work on some of the integration issues that were not fully resolved through the original project. But it's been a great project, and I'm happy to be able to talk about it today. So you could go to the next slide. So I'm going to go through the motivation for the project. So why were we doing a demonstration microgrid of this type at this location? How the approach, how did we approach this microgrid? What were the results? You know, where did we succeed? Where did we find challenges? What did we learn? We learned a lot. I'll say in terms of the way that microgrids are designed and built to deal with both industry, you know, commercial industry, utility, energy markets issues, and then obviously how they can be integrated into the way that the DoD does business. And what are we doing now? What are we doing moving forward related to this project? And why should anybody care? You know, why would this be beneficial to the Department of Defense in general? Next slide, please. So this is an overview of the project and the original concept that was proposed and started the project. So Joint Base Cape Cod is a joint military installation on Cape Cod, Massachusetts. It has Coast Guard, Army Guard, Air National Guard, and others, all on a joint stretch of land. You can see the green area there. The work that we were doing was primarily oriented towards Otis National Guard Base, which is on the east campus at Joint Base Cape Cod. That is an active Air Force installation that does a lot of intelligence work, and they also have done some interesting things with the Air Force Civil Engineering Command in terms of environmental restoration projects and alternative energy. So it was a good, relatively local spot for us. And they had some nice assets we could take advantage of. Like on the left, they have actually 3 large-scale wind turbines on the base. The one that we were working with under this project is called Wind 1, which is a 1.5 megawatt Furlander wind turbine. But the general concept here is that, in the past, the work we've done for ESTCP has been pretty focused on how you can use inverter-based battery storage as a means to better incorporate renewable generation into microgrids, and moreover, how you can multi-purpose the battery storage into grid-tied services that have intrinsic economic value to offset their capital costs and make it a win-win proposition in terms of the functionality you can obtain and then the cost structure associated with actually obtaining that functionality. Go ahead, next slide. So what we were trying to do, or what we did do, is integrate inverter-based energy storage and a new control system that we had developed at Raytheon and first deployed on an earlier ESTCP project at the Marine Corps Air Station in Miramar. And the goal of the energy storage system was to be able to incorporate the renewable generation of the wind turbines and provide these interactive grid services that would create intrinsic economic value to help offset the initial installation costs. And in the ISO New England region, ISO New England being the independent system operator New England, that's essentially the air traffic controller of the regional grid, the most valuable grid interactive service we could perform, and this is still the case today, is frequency regulation. Frequency regulation is a service that different types of generators can participate in, that essentially is trying to buffer out the high frequency variations in load generation balance on the regional grid. And it's managed by the ISO, and it's an open market where different providers can bid into that market. So batteries are one particular type of generator that can be used, or resource that can be used to participate in frequency regulation. And you can see on the left, one of the challenges here is being able to take this automatic generation control signal from an external source and then use it to modulate the battery in a secure way. Because as one could imagine, these military installations are very sensitive to external interfaces and potential security vulnerabilities they create. In addition, we couldn't operate a microgrid off of a wind turbine and a battery alone. The wind sometimes isn't blowing for extended periods of time, and the battery is not a true generator. It only has what energy it has stored. So, we did have an existing diesel generator that was providing persistent generation that was sufficiently sized to power the microgrid itself. But the goal was to minimize the amount of time we would spend actually running that diesel generator. And in doing so, we believe we could achieve a secure and cost-effective approach to using the energy storage and be able to really incorporate the most renewable generation possible. Next slide, please. So from the base's perspective, what does this concept do for them? Why do they care? Nowadays, in particular, for the DoD, it's all about resiliency. And before this project, the state is that they had 4 buildings that had their own dedicated standby generators on the East Campus at Otis National Guard Base. With this microgrid in place, you can support 34 buildings. So the 4 buildings plus another 30 buildings. So it provides a much broader backup power capability than what they would have using these existing 4 standby generators. It also adds the capability to do seamless planned and unplanned islanding. So the idea is presently, if the power were to go down on the base, which it does, they have had a lot of overhead lines and lot of trees and weather can be difficult on the Cape, you lose, your power, then you have to get your standby generators back up, and that takes some time. With this system, with the battery, we're able to transition from a grid-tied state to an islanded state, essentially seamlessly within 60 milliseconds. At the same time, once we're islanded, we want to be able to consume less fuel because we're able to use wind generation to be able to power the island. And then one of the things that we started with the installation was that we don't want to have the microgrid replace the standby generators as the source of backup power. So we want to maintain the standby generators, and in the case of the generator we're using to power the microgrid, we want to retain its functionality as a standby for that particular connected load, but also be able to use it to support the microgrid. So if the microgrid were to go down for some reason, they still have the backup power capability they have today. Go ahead, next slide. On the economic front, one of the key goals of the project was to show that we could achieve good savings to investment ratio and good simple payback. And in order to do that, we need to be able to save money and generate revenue using the assets. So there's several different potential savings and revenue generation streams that we're able to tap into with this system design. Demand management is a particular functionality that is available in ISO New England, where you're paid to curtail your load by virtue of either turning the loads off or running a generator that reduces your apparent load. The utility demand management is similar, except it's requested by the utility instead of the independent system operator. Capacity tag management is something that's, I don't know that it's unique to ISO New England, but is in certain markets where you get charged for the highest power draw that you require over a period of time in the year. And if you can manage that, then you can reduce this capacity tag. And then the biggest thing, frequency regulation, which I described earlier. So these are all different potential revenue streams. Most of these are accessible by virtue of the use of the battery. However, we got lucky on this project in that the generator we're using was built at such a time that it could be grandfathered into the use of its use for demand management in ISO New England. That's not the case anymore. If you were to build a new generator installation and wanted to use it for demand management, it would have had to be a tier 4, more expensive system than what we're using. But we got lucky here with the build date of the engine on the generator. But all of these revenue streams are things that need to be mixed and matched in order to maximize the economic value of the system, in order to make the initial capital investment palatable. Next slide, please. So this diagram shows an overview of the overall system design. On the installation, they have a substation that is owned and operated by the 102nd Intelligence Wing of the Air National Guard, and that substation has 7 total feeders. One of those feeders is called the East Feeder. That feeder powers the Otis National Guard Base East Campus. So what you can see here is coming off of this where it says other JBCC feeders, we have the East Feeder, which has typical instrumentation, protection, and circuit breakers, and then you have a switch that we call the high-speed disconnect switch, which can be used for connecting and disconnecting the microgrid from the larger grid. And what LOGRT stands for is loss of grid ride-through. That is the seamless transition that would occur if the grid was lost, so that the microgrid can be formed without the end user loaders. The load end users to being significantly impacted. Before the microgrid was installed, we had the obviously non-critical and critical loads. That would be the 34 buildings I referred to earlier. The project added in the energy storage system, which you can see with its associated inverter and transformers. And it also added in the control system, which you can see on the right, which is responsible for dispatching the battery during grid tied operation, monitoring and curtailing the wind turbine during grid tied operation. And the reason we had to do that is because in order to get the interconnect with the utility, we had to agree to a relaying scheme that would require a particular level of power import, which is essentially derived from California Rule 21. So we couldn't allow the battery and the wind turbine to generate too much, otherwise it would cause the microgrid to be tripped into an islanded state, which is not really what you want to be doing due to a self-inflicted island that's unpredictable. And then down on the bottom right, like I said earlier, we were lucky in that the generator it was grandfathered into the real-time demand response program as a tier 2. So we didn't have to install a new generator. We could just use the existing generator they had as a demand response asset. So, and coming back to the prior economic slide, we were able to demonstrate participation in frequency regulation, demonstrate the ability to support real-time demand response. And the way that the base had they procured their power, they didn't have access to the capacity tag management, but we are also now, the battery is now enrolled in essentially what amounts to a utility demand response program. So actively right now we have outstanding, or the base has outstanding contracts to do frequency regulation and utility demand response, and pending using the generator, our ISO demand response is pending for other reasons I'll get into later. Next slide, please. So as I said earlier, a key aspect of this project was to generate revenue and cost savings, support simple payback and savings to investment ratio objectives, and the regulation services was the biggest thing. I think, to my knowledge, we were the first demonstration of being able to have an energy storage system and a microgrid on a Air Force installation and conduct frequency regulation connected to the ISO. So that was kind of a big deal. Others have done that plenty in various markets. This battery was actually the third battery that was in the pipeline for the lead market participant we're using. So it's still early in the process of getting batteries into the frequency regulation markets. At least it was when we started the project. It took quite a long in this project, so I think a lot more batteries are now online doing this. And as I mentioned earlier, the diesel generator demand management, we demonstrated the functionality, but we, for reasons again I'll get into later, we aren't currently using that generator as a demand management asset. It's something that's planned for the future, though. Next slide. So this is what the system actually looked like physically. It's several miles across the page here to put things in perspective. The wind turbine I showed earlier is off the page to the left. We can't even see it. The feeder that was built by the Army Guard and Air Guard reservists is about 2.5 miles that goes from the Microgrid Yard that's shown there with the little black square to that wind turbine. The system connects up into the substation that I showed on the diagram earlier, and then the green lines are the east feeder I described earlier, which has been merged with a small portion of the flight line feeder, which is now becomes the microgrid feeder. So really it's connected almost with two feeders on the 7 that I showed earlier, but we have reconfigured the way those feeders are laid out so that we can best service the loads that needed to be serviced. And that really wasn't a particularly burdensome thing to do. It's just a bunch of switches that have to be put in the right position. Next slide. Okay, so for islanded operation, we would be, it's ultimately we are running off the turbine, the battery, and the generator, and we are constantly monitoring the substation in the event of an outage to determine whether we can reconnect. The system has the capability to do both an automated reconnect or a manual reconnect. There's extensive protection to prevent from reconnecting the wrong way at the wrong time. And when the system is islanded, the key functionality is to be able to curtail or is to dispatch the generator as necessary to manage the state of charge of the battery. And if the battery gets too full, curtail the wind turbine. And in addition, due to some unique attributes of the generator or of the battery, I mean, we need to be able to curtail the generator quickly. For circumstances where battery voltage gets too high, for example, we may need to be able to turn the generator off, which I'll show something later that we were able to demonstrate that capability, which was useful in the context of this system. Next slide. So when the system for islanding, the goal was to island for 120 hours using high penetration wind and energy storage, minimizing the amount of diesel generation, maintain power quality to meet the installation needs as specified in the IEEE 1547.4. We were able to demonstrate the battery system running islanded. For reasons I'll get into later, we couldn't actually run the system islanded through the 120-hour demonstration, but that's something that's slated for the future. All the pieces are there. It's the generator became an issue, but I'll talk more about that in lessons learned. Next slide. So when the system is islanded, you can see we are no longer connected to the substation, still connected to the wind turbine, still connected to the microgrid yard, and the east feeder, the microgrid feeder. Ultimately, the only connection that goes away is the one to the substation where the bulk grid is. Next slide. So one of the things we did on this project that we found to be very useful was controller hardware in the loop testing. So for a lot of other industries, doing hardware in the loop testing of software and controls is very routine, certainly for the aerospace industry and where I work, where we do a lot of defense electronics, this is a pretty routine thing. In the power industry, I think it's a little bit more emergent. And the motivation here is really to be able to head off some of the unpredictable interactions between various control systems within the overall system that are difficult to otherwise identify until you're in the field and things aren't working properly and you put equipment at risk. So the racks on the right, you can see we worked with our battery supplier, who's eColt, and Typhoon HIL, who makes the controller hardware in the loop equipment and software, and built a controller hardware in the loop setup of this microgrid, which you can see the simplified one-line diagram on the left, and you can see the substation up the top and a very simplified version of the overall electrical distribution system on the base with the connected battery storage, the critical loads and the non-critical loads, and ultimately, what this culminated with is a series of tests that were done in collaboration with MIT Lincoln Labs per a new IEEE standard that was developed for development and testing of microgrid controllers, the IEEE 2080, I believe it is, or I might be getting that wrong actually, but it says at the bottom of the screen and I cannot presently see it. But in any event, so we went through this testing, and this was, I think, one of the first instances where a microgrid system was tested using controller hardware in the loop to the new IEEE standard, and it was very useful. We definitely were able to head off quite a few integration issues through this testing that would have been much more difficult to resolve in the field. So that was our controller hardware in the loop testing experience. Next slide. So ultimately, we had to build the system, of course, and we did. And what you can see on the screen here is the microgrid yard. The microgrid yard consisted of the battery storage system. The two large 40-foot ISO containers on the right were both contained the batteries we used. On the left, with the heat exchanger on the top, is the 2 MVA inverter and the DC combiner that combined the 2 battery banks, and then the transformer to the left of that that took the 480 volt output and brought it up to the 1247 medium voltage level that the distribution runs at. And then you can't see it very well behind the inverter, and the left battery container is the switch gear, and the switch gear is where we combined all the different loads and generators, and that's how we, where we had the switch that actually connected and disconnected the microgrid from the bulk grid. Next slide, please. As I mentioned earlier, one of the major attributes of activities under this project was to construct the wind feeder that would bring the power from the turbine to the microgrid yard. At the beginning of the project, the turbine was connected to Eversource's transmission system at 23 kV, and the Air Guard and the Army Guard built this 1247 kV feeder from the wind turbine to the microgrid yard. Very significant effort, a lot of new overhead work that was done, by these folks as part of their training. And it was a monumental effort, I'll say. Very interesting to kind of go through that process with them. And Raytheon served as essentially as the general contractor, all the material and supplying them. So it was a very interesting process to go through, but saved the government some money because they were able to, achieve that with training time with these reservists, most of which who are linesmen for the local utilities. So that's how that was built. Next slide. So one of our focuses from Raytheon was the control system. The control system was comprised of obviously our software that does SCADA level control of the microgrid, and then the endpoint devices which were providing protection. One of the main issues in these microgrid or a lot of these industrial control systems for DoD uses is that they use protocols and techniques that are not particularly secure from a cybersecurity perspective inherently. So you have to go and do things to make the networks that you use to host the information more secure. And that's what the racks on the bottom there are doing. They have firewalls, they have UPSs and switches and or routers to essentially protect the core network from external compromise. So those existed at all the locations that we installed connection, and then aggregated all the information back at Building 971, which is a civil engineering building on the base where you could actually monitor and control the overall microgrid. Next slide. So this shows additional control elements that we built. The control rack, which is located in the communications building where the controller is, and again, more networking equipment. Up on the right is the relaying that we installed to meet the utilities requirements for the interconnection at the substation, and then at the bottom right is another one of the control rack boxes that we installed to provide the endpoint protection to the microgrid network. And the microgrid network was built on existing dark fiber they already had, so we didn't have to we didn't have to ride on any of the existing networks that they had at the base, which was actually a big help in terms of having an installation that was easier to get through cybersecurity approvals due to the no possibility of data intermingling between our microgrid network and any of the other military networks that would be running on other fiber elsewhere in the base. Next slide. So this slide has a video. which I don't know if it'll work, but nope, let's see. Oh, it is working. So what this video is showing you, which is not particularly exciting, I suppose, without sound and all, is what we did with the generator. So the generator in the bottom right is it's a standby generator. It's a 1.6 megawatt Kohler, and what we ended up doing was to install modifications to the transfer switch they already had, which allowed this standby generator to be used in a grid parallel mode of operation, so it could backfeed the distribution system to power the microgrid. The neat thing about it, which the video actually shows and just did, is when you are operating the system, if the microgrid were to fail, or for some reason you would need to curtail the generator because, for example, the battery voltage was getting unpredictably high, you can fast curtail that generator or trip it, and it will continue to power the building that's connected to, and it won't shut down, but it'll be disconnected from the microgrid. So this was a key feature that we thought was clever about this design, is that by simply modifying the controller on the transfer switch and making some changes to the putting in a new governor and reprogramming the speed controller on the generator, we were able to upgrade that generator to be able to provide parallel operation without taking away any of its capabilities to provide dedicated standby power on to the building. And in fact, on several occasions we had situations where we were testing, and the parallel operation we had an issue with, and the generator tripped over to powering the building, and did that seamlessly without an issue. And that's a big deal, because I think a lot of the folks who are the end users of these systems, they just want to know that the power is going to be there all the time. Whether the microgrid's providing it or the generator itself is providing it is less important to them. They just want to know it's going to be there. And we were able to demonstrate that was definitely a viable solution using this approach. Next slide. So as I mentioned earlier, a major aspect of what we were doing in terms of grid tie performance was frequency regulation. So as of the time I constructed this presentation, we had the battery in the ISO New England frequency regulation market for 60 days, making about $500 a day, providing frequency regulation at 1 megawatt. Moving forward, our plan is to step that up to 1.2 megawatt, 1.4, or maybe even as high as 1.6. The battery is capable of 1.6, but we may have thermal limitations operating at that regulation capacity. This is the primary day-to-day use case for this battery, is to run frequency regulation and generate revenue that way. So most of the time, this system will be doing that. Next slide. And this is a typical what the ISO calls a Regmon report, which shows the signal that was commanded to the battery, and shows the battery's response, and then the various limits that determine how the battery is scored. In order to get compensated in this market, you have to perform to a level that allows you to be scored reasonably well. And the battery actually, with the exception of a few periods where we had known issues with connectivity or other battery-centric issues, performed very, very well in the mid to high 90s, 90% scoring range, pretty much all the time it was up. So we were very encouraged, at least the 1 megawatt regulation capacity, the battery would perform well. Next slide. Cybersecurity, of course, is a big deal for the DoD, and was quite a process, I'll say, on this project. We started off developing an interim authority to test submission, and submitted that back in April of 2018. We got some comments back on that package from the authorizing official, and none of them really substantive, but more administrative in nature. We completed a response to those comments, and didn't really require any changes to design. But when that happened, Hurricane Michael hit Tyndall Air Force Base, where the AO or where the folks who actually do the security controls assessment reside, and the AO left the role. Therefore, we were kind of left hanging. So in order to gap fill, we got some local approval from the wing commander at the 102nd Intelligence Wing through May 2019. And in the interim, we worked with the STCP and made the decision that we would do a self-attested ATO submission, which is maintains the system under the control of the contractor, which is a different set of requirements than the DoD RMF, which is ultimately where this system needs to go in order to be under government or DoD control and be fully authorized to operate persistently. So where we are with cybersecurity right now is the system is under contractor control and meeting those requirements. And we are confident based on the design and our original IATT review that our design will pass muster for full RMF ATO once we actually hand the system off to the Air Force, the Air Guard, which is planned for 2022. Next slide, please. So in terms of things that were for first here that we're proud of and what this project did, this was the first microgrid that Eversource Westwood, which is a regional office for Eversource, who is the utility for Otis National Guard Base and Joint Base Cape Cod, had ever dealt with. So they were very accustomed to installing large photovoltaic installations, but they really didn't know, how to deal with a microgrid, what it was, what it really meant to them. So there was quite a process for them and us, I'll say, to understand and reconcile what we were trying to do with what they're used to. Sounds not that exciting. It is quite interesting when you're trying to do something different than what the utility is used to and have to figure out how you can meet their standard practices and requirements. But we were able to overcome that and do it in an affordable way. So that was the first time they had actually interconnected a microgrid into their utility connections. This was the first time that ISO New England had allowed a battery performing frequency regulation, otherwise called an alternative technology regulating resource, to provide frequency regulation behind the point of retail delivery. And what that means is typically when people install batteries in ISO New England, they have to be directly connected to the utility at the point where the utility meters the demand and the energy consumption of the installation. For microgrids, especially military microgrids, this becomes kind of impractical because a lot of the time you can't site your equipment at that point where you're being metered by the utility, or you're using existing equipment where you have to move it and electrically connect it differently. It just becomes impractical and unaffordable to do. Moreover, if you want to use the asset as part of a microgrid, you really want it connected within the microgrid, not directly to the utility, because otherwise it's not going to be able to support that microgrid. So negotiating with the ISO and satisfying their concerns that we wouldn't be playing any games with the way we were moving power around behind where they had direct visibility point of retail delivery. We came to an agreement, and we set that precedent where now we can have batteries in ISO New England behind the point of retail delivery that are supporting microgrids and providing frequency regulation services. And as I mentioned earlier, to our knowledge, this was the first time that there was a battery energy storage system on an Air Force facility performing frequency regulation with an external connection driving the system. This also, another thing that we think was the first was the completion of the IEEE 2030.8. That was the proper spec name. Testing using controller hardware in the loop techniques. And as of the present moment, we have the paradigm that we've pursued in terms of continuing operations of the system was to have third-party incentive-based contracts. So Customized Energy Solutions is the folks responsible for the battery's participation in the markets, and C-Power is responsible for the utility demand response and the ISO demand response activities. And these folks basically get paid when the assets are up and producing and generating revenue. So the DoD is in a good position to be able to just support these entities and not have to take responsibility for bidding the equipment into the market, things they just don't have expertise for. So I think the business or the setup here from a pure business standpoint works very nicely because these third-party energy services companies are able to do what they do well, and the DoD gets the benefit by virtue of their success with these assets when they're not being used for resiliency purposes. Next slide. Okay. So key lessons learned. So we did learn quite a bit in the process here. The utility, the independent system operator, and the government had varied perspectives on what should be allowed, how things should work. I described earlier, how the way that we wanted to configure the system with the battery, behind the point of retail delivery was something that the ISO was strongly against for quite a long while because of experiences they'd had, I think, in the past where people had done those types of things and they had not provided the desired capability because they were, say, for example, using multiple batteries and pushing and pulling power between the batteries behind the point of retail delivery in ways that weren't creating the aggregate desired effect, for the grid. So figuring out how to make sure we could retain the benefits of the microgrid, but still, satisfy the concerns of the ISO in that instance was interesting and challenging. But ultimately, we definitely got to a point where we could resolve those competing interests and created some clever schemes for metering protection and control, and in order to do that. So that was a key thing to look at for anybody who's trying to create a system like this: is how are we going to actually to handle these competing interests. The cybersecurity aspect, as I mentioned earlier, was quite a winding road. A lot of that had been changing from a policy and process standpoint during the project. And ultimately where we're at now, I feel pretty comfortable about. You still have to go through the final step of transitioning to government ownership and actually executing the risk management framework authority to operate. But the design has already been vetted, and we feel comfortable that it should be able to pass muster once we get to that point. And another key issue for us that really was our biggest holdback is the government policy aspect. So there was a Air Force instruction that we confronted early in the program and thought we had kind of put behind us, that basically said that you cannot use standby generators attached to critical loads for anything other than that attached critical load. And there was a competing Department of Defense instruction that basically said, we encourage you to do the exact opposite and use your generators to support loads as broadly as you can, and use existing distributed energy resources. So those two particular instructions, one being Air Force, one being DoD wide, were not well synchronized at all. And ultimately in the project, what that ended up doing to us in the project was having us so we couldn't use that generator to island the system towards the end of the project, which was really a shame. The good news is that as of October of 2020, right when the project ended, actually, a new instruction came out that does provide a little bit more leeway, I'll say, as to how you can use these standby generators for microgrids and things other than the pure standby backup generation purpose with the connected building. But that issue is not fully resolved. It's still something we're working right now with the base. And then more broadly, there was no Air Force policy on microgrids whatsoever, which I think the challenge there is, you talk to folks in the Air Force and they're looking for a line item that covers the type of equipment you're trying to transfer to them, and you tell them it's a microgrid, and they kind of go cross-eyed because they have no policy or guidance as to what that really means. So, I think a lot of, the government is a big organization. I think they're still catching up with the technology in terms of microgrids and how they're going to work with them. Next slide. Another key issue on this project was transition from demonstration to sustainment. So, we need to be able to, ultimately, Raytheon can't own this equipment forever. So we need to be able to transition it to the Air Guard and the Air Force. And the way the military operates, the processes to resource such things have to start significantly earlier than these demonstration projects would desire them to. So getting a budget line item into the plan for the installation that's going to take ownership of the property is kind of a big deal, and it's still something that we're working with the Air Guard on this project. The resourcing, the system. So this system, from a cybersecurity standpoint, has some fairly significant upkeep requirements, and that is something that ultimately needs to be kept in mind as we as we move forward with the project. And at this installation, they have pretty limited capability to do the cybersecurity and information assurance upkeep. And then somebody's got to actually just maintain the battery systems. And so that's something we're actually going to be, we're still working at ESTCP to provide those services to Raytheon with subcontractors until such a time that we transition the system over to Air Force Civil Engineering Command and the Air Guard to continue to resource the operations and maintenance and cybersecurity posture maintenance. And another big challenge in these military microgrids is leadership turnover. In the military, every 2 to 3 years, leadership will turn over. And at this installation, they're very much focused on the mission, and as I'm sure they are at all installations. And we, during this project, we had started off with very strong leadership on the government side from the sponsor, who was deputy base civil engineer, and then he ended up getting a job in the private sector. So reacquainting folks on the installation with the project and kind of reselling the value of the project was an ongoing thing as personnel turnover occurred. This project, we started in the beginning of 2017. So during 2017 to the end of the project, October 2020, the market for frequency regulation, for example, changed quite a bit. The value of frequency regulation went down. It's still the largest value stream for this system, but it went down notably. So the market dynamics are significantly faster than the way these DoD projects can be executed, and that's something that you need to be mindful of, because if you build your whole business case around something that could change over the course of a couple of years, that can become an issue on the economic front. Next slide. So path forward. So our planned path forward is we have a follow-on effort to operate the system for a year and characterize the cost and performance of the system over that year, build up resources for sustainment of the system. So, we have already had checks coming from Customized Energy Solutions, the Air Force Civil Engineering Command, from Frequency Regulation Services, and those are being used to build up the coffers. So the system will basically pay for its own maintenance, when we turn it over to the Air Guard. As I mentioned earlier, we're still making sure that there is a path to transfer the equipment as real property to the Air Force or the Air National Guard. And then we need to make sure there is resources in place for the cybersecurity and information assurance posture upkeep. Ultimately, the system will be transitioned over to Air Force Civil Engineering Command. They currently own the contracts to maintain the wind turbines and the installation restoration program, which does the groundwater reclamation. So they're very familiar with how to run energy projects, and we saw a good fit there with them being able to take the revenues from this system and then turn those around and support contracts that will initially set up under the extended demonstration period, and then support the 102nd Intelligence Wing with their submission of the RMF ATO package to finally get the system completely authorized as a government-owned industrial control network system. And next slide. Because of the generator being taken away, I'll say, by virtue of this issue with the AFI compliance, we really weren't able to do much in the way of islanding beyond showing that We couldn't really island the system and run it on a consistent basis with just the generator, without the generator. The battery is a 1.6 megawatt, 1.2 megawatt hour battery with a viable state of charge range of roughly 30 to 80%. So the effective energy in the system for a 1.2 megawatt peak load is relatively small, and we wouldn't be able to island the system for very long simply off the battery alone. The way the system was designed was to at peak load was to start the generator and base load it, when the system went into an islanded mode. So once we lost the generator, we really couldn't do a lot there. But because that generator was dramatically oversized for the building it's connected to, the 102nd Intelligence Wing is now replacing that with a right-sized generator and attempting to gift the DCGS generator, that's the name of the installation, to the microgrid and relocate it at the Microgrid Yard. So that is currently underway, and we would be looking to complete the integration of the generator in its new location under a follow-on project, where we would also finalize the connections to the wind turbine and do a final integration demonstration operation. So because of that generator issue, we weren't able to get as far as we wanted on our islanding objectives, but all the equipment's there, and it's really just getting that generator squared up and integrated in the location to complete those objectives. Next slide. So benefits. So why should anybody care about this project at all who's not a resident at the at Otis National Guard Base? Like I described earlier, new precedents. So we showed you can go and connect a battery on a military installation, provide cybersecure grid interactive services, and generate revenue doing it. And so it's been done on this project, at an Air National Guard Base. While you may get pushback from the various stakeholders in constructing such a project, the things can be reconciled, and that can be made to happen. And installing a microgrid doesn't mean that you have to throw away your standby generators and feel like you are giving away a level of security, energy security you're comfortable with. But the microgrid can be layered on top of those standby generators, and you can have 34 buildings instead of 4. And in essence, depending on this one, we only used 1 generator of the 4, but you could, in some other systems, you can connect all 4. So if you lose 1, you still have 3. And you still have those 4 as with a dedicated standby capability as well. So it's not an either or, it's a both proposition. And in terms of operational benefits, Otis National Guard Base now has a battery system that is capable of providing these services, and will soon have the generator up and full microgrid in its final configuration is the plan. We're going to be continuing to run the battery through frequency regulation over the next year, and show that that's going to be a sustainable value proposition for the installation that pays for the operations and maintenance, and allows the system to persist beyond 2022 when the extended demonstration is complete. Next slide. And that was my last slide. So I think I'm pretty much right on time. So I think we're ready to go on questions.
Wonderful. Thank you so much, Dave, for the presentation. I want to remind our audience at this time that you can submit questions to Dave using the Q&A box, which should show up if you hover your mouse over the Zoom menu. Our first question, Dave, is from DoD. Does the battery energy storage system offer any power quality benefits or ride-through?
Yes, we'll ride through, yes. We weren't using it for power quality purposes per se, in terms of, during grid-tied operation. They had, for example, capacitor banks installed to improve the power factor of the installation already. But if the battery sees a power quality deviation that goes beyond it's roughly per the IEEE 1547 requirements, then it would trigger the system island, which is what you'd want to do, because a grid failure, the system doesn't really know a grid failure from power quality deviation when it exceeds the IEEE 1547 interconnection requirements. So I guess that's a long way of saying absolutely yes. If power quality varies, the system will treat that as if power is being, if there's a power loss, provided that power quality variation is outside of the allowable limits.
Thank you, Dave. And your volume is going in and out a little bit. If you could stay right near your microphone, maybe.
Sorry, I'm attempting to be close to my computer.
Yep, no problem. So we received a number of questions about the Colt battery technology. Could you provide some more details about it? First, why was it chosen and what kind of battery is it?
Yep, so the battery it's a lead carbon battery. It's the battery itself is called Ultra Battery. It's made by Colt, who is a subsidiary of East Penn Manufacturing, or was a subsidiary. Unfortunately, recently they became a victim of the industry downturn due to COVID-19. But we chose that battery because it was a fully commercial battery technology, meaning they had a megawatt, 2 megawatt, I'm sorry, multiple megawatts of deployed capability, but it wasn't commoditized in the way, say, lead lithium ion is. It had some comparable performance characteristics to lithium ion, in particular for functions like renewable buffering and frequency regulation, but was arguably in some respects safer, being a lead acid chemistry and not a lithium ion chemistry, so less prone to flammability and easier to recycle, things of that nature. So we wanted to kind of create a system that demonstrated that technology, not just the overall microgrid concept, but not use a fully commoditized battery technology on this project. And it has worked out well to the extent that they've, the battery has performed very well on the project. And Ecolt was really tremendous to work with. So that's how we chose that battery.
Okay, great. The next question is about, with respect to the battery, did you see any observed degradation due to cycling or any lifetime impacts, for example?
So we just had our first battery fail on us. I think there's I can't remember. I think it's about 900 batteries in the installation. But we've only had one that is dropped, that has shown signs of fatigue, which may be more of an infant mortality than a long-term degradation. The rough expectation is about 10 years of service doing persistent frequency regulation. However, the battery manufacturer, like I said, they're largely, they don't have, hundreds of megawatts of installed capability that's been running for years and years and years. So they don't have a real, they will not, it's hard to get them to say with certainty, how long the batteries should last beyond, throughput that they've measured on some systems they have at their own facilities. But we have not really seen much in the way of degradation beyond this one battery. And ultimately, our expectation is that the system is going to perform for the next, 5 to pressing, 10 years at, in the use cases that I've already discussed.
Okay, thank you. Next, we have a couple of clarifying questions. Is the battery directly metered for performance and settlement with ISO NE frequency regulation? Okay.
Yes, it is. Yep. So we have metering, revenue grade metering on the battery, and then we have secondary metering elsewhere in the system that Customized Energy Solutions is able to use to satisfy the ISO concerns that we're operating the battery properly behind the meter.
Okay. And was wind power the sole source of energy for the project?
No, we had the generator. So, I mean, and then when we're grid tied, we're going off the grid.
Okay. Next, could you talk a little bit about the standards used in the design of the microgrid? You mentioned testing to IEEE 2030.8. Was IEEE standard 2030.7 used in the design?
Yeah, so 2030.7 is the microgrid controller requirements, and 2030.8 is the testing standard. So in order to pass 2030.8, you'd have to be generally designed to 2030.7. So that's how we did it. The standard requirements out of IEEE 1547 for distributed generation interconnect were used. And then there were a bunch of requirements that the utility put on us, but it was, for the electrical equipment, it was largely industry standard specifications. And then the kind of the newer part with the microgrid control was the 2030.7, 2030.8. And then there was a whole bunch of Air Force instructions and Unified Facility Code requirements that we had to meet through the design that were specific to the military. So those are the types of standards that were used.
Okay, great. And regarding those standards on a higher level, do you know whether the other service branches have other policies regarding microgrids?
I don't know. I haven't studied that. I believe the Army very well may. I know there's the tactical microgrids standard that's been worked, which is more so tactical than it is installation, CONUS installation. But we've done other projects for the Marine Corps. There were several years ago, there were no specific standards or requirements or standards around microgrids for the Navy and the Marine Corps at the time. But I'm just not up to speed with the other services well enough to say with any great certainty. So.
Sure, understood. The next question is from the Army Environmental Command. Could you tell us how long it will take for the system to pay for itself, or give any other kind of higher level return on investment description?
Yeah, so I believe the analysis that we did on the design was showing somewhere like 8. Our original goal was 5-year simple payback, and I think the actual as produced design at the end, when the latest economic analysis done, was more like 8 to 10 years. So way the system's operating right now, just off the frequency regulation, it's a bit longer than that, and that's going to be in the final report. I don't remember what the specific number is, but a system like this, I mean, getting to 5-year simple payback, which is the original goal, is pretty difficult. Getting to a 10-year simple payback, I think is definitely in the range of achievable. So that's the kind of payback period you're looking at with this type of a system.
Okay.
Now I will also comment that that also is a large function of the battery technology we used here. If you go with a more commoditized, lower cost battery technology like lithium ion, it probably actually gets better than that. So.
Okay, understood. Thank you. Next, did you perform any risk and resilience analyses to inform the design of the microgrid, specifically as they relate to climate hazards?
In short, no, we did not. There were other analyses we did on prior projects, working with the National Renewable Energy Lab, looking at the costs associated with achieving the level of resiliency provided by a microgrid to try to monetize the value of the microgrid. But we never looked at things like climate and tried to figure out how many outages we would expect in a year, or did any analysis to that end. No.
Thank you. How did the price of frequency regulation change during the course of the project? Did you track that?
Yeah, I mean, frequency regulation is difficult to. The way that the compensation is determined is fairly complicated. So it's not like it's you pay X cents per kilowatt or what have you, like demand or capacity payments. It's so it's we didn't have like a constant ongoing knowledge of how it was varying, but when we started the project, we expected that the revenue associated with frequency regulation would be in the range of $300,000 to $400,000 a year, and when we completed the project, it had gone down to $200,000 to $300,000 a year. So it reduced notably, just due to the way the frequency regulation market had worked out, and a lot of that is, I suspect, due to the market getting more saturated with more resources to provide the service. So there's just, it's a supply and demand thing is my suspicion, but I'm not an energy services expert, so I can't say that with any certainty.
Sure, understood. And does the system have a reliability rating with respect to the microgrid?
No, we didn't do any formal reliability analysis on this system design. For another project with several other installations, we did develop a reliability analysis. Well, we didn't develop it. The National Renewable Energy Lab developed a reliability methodology that we use to analyze other systems, which was basically looking at the probability of carrying the critical load as a function of time based on the constituent reliability of all the components in the system. We just never performed that analysis on this system. The goal of this project was to design and demonstrate, the system concept and then collect performance on it. So doing a rigorous reliability analysis just wasn't part of the original scope of the project.
Next, questions about the generator. And the comment was that the findings from the generator modifications were a great result from the project. Can you talk about whether they were at all part of the scope of the project to look at that, or did that arise as the project proceeded?
So we originally started off under the assumption that we were going to follow the approach that was taken on another military microgrid project called Spiders, where they used standby generators and connected them through a bypass breaker to do something similar. But the difference was, we would have had to put in, an additional breaker, a lot more equipment, and potentially not have the ability to trip the generator back into a standby mode of operation if we were to encounter an issue with the microgrid. So when we got into the design, we found that modification of the transfer switch, like we ultimately implemented, was going to be the more straightforward way and more beneficial way to do it. So that's the way we went. So I think that's one of the aspects of the project that worked out better than what we originally proposed, as that design option became viable.
Okay, thank you. We have one last detailed question before we move to one or two last general questions. Was there any consideration to put the cables to the wind turbine underground? And if they weren't put underground, what prevented that?
Yep. So cost, essentially, it's, I think it was 2.5 miles or something of distribution, new distribution installation. And we did have sections of it that ran underground where we had to cross, under roads, for example, because we couldn't go overhead roads because of other detailed reasons. But trenching and installing the, ducting to install that cable underground would have been a much bigger task than the overhead that was installed. So the decision was made early that we were just going to use it as an overhead installation, and ultimately, within the fence line of the base, they've gone and moved a lot of their overhead distribution underground to protect it better. But for something like a wind turbine connection, I don't think the cost likely would not have been justified, since that's not a mission critical connection.
Okay, thank you. So now the first general question for you is, what are you working on next with respect to this project and other DoD microgrids?
Yeah, so Raytheon has continued to work in this space, and we have a few ongoing projects where we're still focused on battery storage microgrids and controller hardware in the loop methods to develop and demonstrate these types of technologies. And one of the limitations on this system is we have one battery that, when the system is performing, if that battery fails, then the whole system fails. But other concepts we're pursuing allow us to distribute that functionality to multiple batteries in order to provide similar levels of resiliency to network diesel generators and diesel generator centric microgrids. On this project, as I mentioned, we're moving into extended demonstration of the battery doing frequency regulation, and hopefully, with the generator recited, completing the aspects that the additional islanding demonstrations we weren't able to complete due to the generator issues we had. So we're still active in the space and looking for ways to build on what we learned to this project to ultimately keep improving the technology.
Excellent. And Dave, is there a last message that you would like to leave the audience with today? One final takeaway.
No, I'd just like to thank ESTCP for the opportunity to do the project. It's been a really exciting and fun project, and we look forward to continuing to support Otis National Guard Base and the Air Guard to keeping this system operating, and hopefully have it be a model of some things that other installations could do if they were so motivated.
Great. Thank you so much, Dave, for the presentation and for answering all of the questions. We really appreciate it today.
Thank you.
And the next webinar in the SERDP and ESTCP series is on Thursday, June 3rd. It's in the Environmental Restoration Program area, and will focus on DoD-funded research efforts to address PFAS analytical challenges and opportunities. Registration is open for this webinar and for other webinars as well, so please visit the webinar webpage to register. And before we conclude, I would like to remind you that both the audio and a copy of the presentation for today's session will be archived on our webinar webpage in case you would like to refer to them in the future. And we would appreciate it if you could please take a moment to complete the survey that will show up on your screen at this time. This concludes today's webcast. Thank you.